Hi everyone, I'm Vishal. I'm presenting our work on estimating leaf water content using remotely sensed hyperspectral data. So this is a joint work with Rahul Raj, Rohit, and Professor Adinarayana from IIT Bombay. So the aim and motivation of this work is to identify plant water stress because it is an important factor that determines the growth of a plant, its productivity, and its yield. So early identification of plant water stress and leaf water content enables us to take suitable corrective measure in early stages of plant growth, which enables us to improve the productivity and yield of the crop. So this work estimates leaf water content to further estimate plot level statistics. So we will go into that sooner. So plot level statistics would give us almost every pixel level granularity. We would have the data to make predictions on the status of the crop and whether we would need to improve any aspects of the irrigation process or other processes so that the yield can be saved if it is under any sort of water stress. So further, this work is one of the first works to estimate leaf water content by identifying pure pixel water sensitive indices in the 400 to 1000 nanometer range, because this is a more realistic range in which leaf water content can be, hyperspectral images can be captured, rather than more expensive variations which goes further than 1600 nanometers. So the range of the spectrometer data here is in the 400,000 nanometer, and we also capture UAV-based hyperspectral images in real outdoor environments at multiple days after sowing. So we will look into how we identify indices in the spectrophotometric data where we have ground truth leaf water content information, uh, which is the true ground truth, and then how we use pseudo ground truth based mapping to train our UAV captured hyperspectral images. So this is our methodology. So we have our data set in the spectrophotometry captured by the spectrophotometer. So we identify 11 indices that correspond to water stress and leaf water content. Then we utilize these identified indices and train on the hyperspectral images that are captured by UAVs. And then we use the pseudo ground truth using another method that we have developed to identify uh, where each plot level statistics. And finally, we predict the water stress status of the crop. So first, we will look into how the 11 indices were identified. So we would give an overview of our data set. So this is the cropland where there are three different types of treatments that we look into. So one is nitrogen and water stress. So for each, we have three types. So I1 here would represent water stress. I2 would be medium water stress, and I3 would be sufficient or just enough water provided to the crops. Similarly for nitrogen, so in this plot, we can see what I1, N1, and N3 would, each of these six treatments would represent. So we capture the spectrophotometer data using the SpectraVista GR, and three replications were captured from each of these 27 plots on multiple days after sowing. Days after sowing is just a metric that says that gives us an idea on how many days have passed after the crop has been sown. And there's a critical date of 36 days after sowing, where the crop is in the tasseling stage, where after which it is difficult to induce any corrective measures to improve the growth of the plant. But any time before days after sowing 36, we are able to identify the water stress and also apply corrective measures so that the yield is not affected. And we also capture, this image is the UAE captured hyperspectral image, and we will look into that now. So in identifying the different indices, we look into different literatures, and we also identify a secondary water sensitive bands in the 950 to 970 nanometer range, which directly decrease the water index in the plant. So we also use NDVI and green NDVI and red NDVI because under variations in the foliage color, these conditions and the green and NDVI are more water sensitive. So we use the NDVI red and green bands, and we also identify that the water index in the 950 to 970 nanometer band. And as stated before, we only go up to 1000 nanometers because that's a more realistic capture range than using more expensive equipment. Further, uh, we have we identify these bands based on our coefficient heat map of coefficient of determination. So here we plot the bands and identify the maximally correlated ranges of in values so that we can identify the indices that directly correspond to water stress. So from this analysis, these are the 11 indices that we have identified. And these 3 indices correspond to the ones we have identified in the 950 to 970 nanometer range, as well as the 400 to 1000 nanometer range based on our heat map experiments. And the other indices are identified from literature. So we then so we then train multiple stacked regressors on the data, and we use a pseudo ground truth, which is based on another work that identifies the range of indices and generates synthetic data. That synthetic data is used to train the model to identify the water content at 1 meter by 1 meter range. So this is not the granular pixels that we have for predictions here of all these plots. So these are 1 meter by 1 meter plots each. And what we find is this is a good approximation or for a pseudo ground truth for every pixel in this region, so that we can train our regressors on the UAV captured hyperspectral images so that they are able to predict the leaf water content. And once we identify the leaf water content, we just use a simple threshold of 79% for days after sowing as 36 as the critical data to identify the exact the status of the crop on 36. So any crop that is greater than 79% would not be water stressed, whereas anything less than 79% would be water stressed. So this is our result and comparative analysis. This is our plot image captured. It is the RGB image, and this would be the pseudo ground truth that we use from our previous work. And this is the leaf water content plot that is obtained when a model is trained on the UAV based hyperspectral image. And we see that the pseudo ground truth enables good generalization performance, as the water stress plot here verifies. So we use the actual ground truth that is obtained from destructive distillation to verify the leaf water content and the water stress status for days after sowing at 36. And to further extend, we also show that using the 3 indices that we identified in this work, in the course of our work, we find the maximum R square and RMSE. And using all 11 indices, including the 8 indices from the literature, we find a slight increase. So this is the basis of used in this research. And finally, we talk about temporally varying leaf water content estimation. So this is the plot image. This is at DAs 36, 63, and 115. And we plot them on a single scale, and we experimentally verify that using the indices that we have identified, using the spectrophotometer data, and then using those indices and training a model for different regressors in the hyperspectral UAV captured data, we are able to identify the water stress status of the crop so that we can apply corrective measures to improve the yield. So yes, that would be the end of this presentation. So are there any questions?
Thank you, Vishal, for the interesting talk. If you have any questions, you can write them in the chat and I can read them out for you, or you could raise your hand. I would maybe start with the question, Vishal. What do you think, how could you explain only the small improvement you get from using the top 3 indices that you hand selected to the 11 indices. Does this have something to do with like some kind of cross correlations or something between the indices that are then added, or what do you think?
Oh, yes. So in this in our coefficient of determination, we find three indices as we mentioned, the NIR1, red, blue, and water band in this work. So these indices correspond to the three indices here, and we see that by just using the 8 indices that are identified from the literature, which would directly correlate with water stress, that's NDVI, green, red, MTVI2, and these 8 indices, we only obtain about 0.65 R square metric. Whereas using the three indices we've identified, we obtain 0.925. And when we combine the two, yes, the correlations would come into play and we get a slight increase in the result.
Okay, that's interesting. Are you aware, is there any other work that actually tries to do some kind of maybe end-to-end approach where you just pretty much give as input the hyperspectral data in a very raw form and try to estimate the leaf water content?
That would be a difficult thing to do because there is no, it is very difficult to obtain ground truth for every leaf and every pixel of the graph. So that is the reason we go with 1 meter by 1 meter granularity and then use that as a pseudo ground truth to train our metric. But it would be possible.
Would this type of analysis also translate well to these applications we saw earlier by Cyril Stachnis, where you would have a robot navigating just a few meters over the plant? Or does this rely too much on the wavelengths you detect through remote sensing?
No, it wouldn't depend on the wavelength. So we captured the one hyperspectral image from 50 meters above. So it would depend on the sensors that are being used. The wavelengths captured would be mostly similar.
That's very interesting. Thank you, Visha, for your talk.